NCRT, JEE Main and NEET purpose, the most important points of P block elements we'll discuss. Group 13, 14, 15, 16, 17, 18. In 6 videos, we'll complete all this. This is NCRT book. Thank you NCRT for providing this. The valence shell electronic configuration is NS2 NP1 to 6. First point. The difference in inner core of elements greatly influences their physical properties as well as chemical properties. Whatever the important points are there, I have made them and highlighted. Okay, please see that line. The maximum oxidation state shown by a p block element is equal to the total number of valence electrons. If valence electrons are 3, the maximum state will be 3. If the valence electrons are 5, the maximum state will be 5, like phosphorus group. Here, inert pair effect, the occurrence of oxidation states 2 units less than the group oxidation states are sometimes attributed to the inert pair effect. These are general things. See here, group 13 plus 3 oxidation state, 14 plus 4, 15 plus 5, 16 plus 6, 17 plus 7, 18 plus 8. Other oxidation states for 13th group plus 1, 14th group plus 2 minus 4, 15th group plus 3 minus 3. All these lines you need to remember. Then it is interesting to note that the non-metals and metalloids exist only in the p block of the periodic table. This is actually a wrong statement, because here only in all the groups it will mention aluminum is a metal, like that it is mentioned. Okay, now so metals, non-metals, metalloids are there, but this it should be corrected. Okay, there are some mistakes in NCRT also. Plenty of mistakes are there. We'll check one by one all those. In fact, the heaviest element in each p block group is the most metallic in nature. That means last element. The non-metal oxides are acidic or neutral, whereas metal oxides are basic. This is a rule. Non-metal oxides are acidic and are neutral generally. Neutral are only 3: carbon monoxide, nitric oxide, and nitrous oxide. General remaining all are acidic. Metal oxides are basic. This is known to us. Yes. Here you see the second period elements of groups, p groups, starting from boron, are restricted to a maximum covalency of 4, whereas third period can expand up to 6. BF4 minus 4, ARF6 minus 3, that is 6 coordination number you can see here. These are directly coming in exam. The first member of a group differs from the heavier members in its ability to form p-pi multiple bonds to itself, like carbon-carbon, and other elements, that is carbon oxygen, carbon nitrogen, all these direct statements will come. This type of pi bonding is not particularly strong for the heavier p block elements. The heavier elements do form pi bonds, but this involves d orbitals, d pi p pi or d pi d pi. Again, straight point. In +5 oxidation state, both nitrogen and phosphorus form oxoanions. NO3 minus 3 coordination with pi bond involving 1 nitrogen p orbital, and PO4 minus 3 4 coordination involving s p d orbitals contributing to the pi bond. Now coming to the group 13. Boron is a typical non-metal, aluminum is a metal. Gallium, indium, thallium are metallic in nature. Boron is a fairly rare element, mainly occurs as orthoboric acid H3BO3, borax Na2B4O7 10H2O, kernite Na2B4O7 4H2O. Matching type of questions you can expect. Boron 2 isotopes B10, B11, 19%, 81%. Aluminum is the most abundant metal and third most abundant element in the Earth's crust after oxygen and silicon. Bauxite Al2O3 2H2O and chrylite Na3AlF6 are the important minerals of aluminum. In India, it is found as mica. No need of these places, don't worry. Yeah, we'll come to this. The outer electronic configuration of these elements is NS2 NP1. Fine. Boron and aluminum have noble gas core. Gallium and indium have noble gas plus 10d electrons. Thallium has noble gas plus 14f electrons and 10d electrons. Because of this, there are some differences. Atomic radius of gallium is less than that of aluminum. Okay, now regular points I am not taking. I am just taking the important lines. The presence of additional 10d electrons offer only poor staining effects. Gallium 135 picometers, aluminum 143 picometers. Down the group it should increase, but it is decreasing. Ionization enthalpy. The observed discontinuity in the ionization enthalpy values between aluminum and gallium and in between indium and thallium are due to inability of D and F electrons because of low screening effect. Point. The order of ionization enthalpy is as expected. H1, H2, H3 if you are having, H3 is always greater. Electronegativity. Electronegativity first decreases from boron to aluminum, then it will be same. Okay, now. Yeah, boron to aluminum it is decreasing, then increases. Boron is 2, aluminum is 1.5, then 1.6, 1.7, 1.8. It will be increasing. This is because of the discrepancies in atomic size of the elements. There will be a table, beta. We will go with the table. Yeah, you can see here 2, 1.5, 1.6, 1.7, 1.8 electronegativities. Ionization enthalpies also you can check. Aluminum and gallium. Down the group it should decrease, but gallium is more. Indium and thallium it should decrease, but thallium is more. Melting points also. From boron to gallium it is decreasing, then it is increasing, but the highest is for boron. Chalo, some important lines we'll check up now. Boron is non-metallic in nature, hard and black color solid. It exists in many allotropic forms. Boron has unusually high melting point because of strong crystalline lattice. Rest of the members are soft metals with low melting point and high electrical conductivity. Gallium with unusually low melting point 303 Kelvin could exist in liquid state during summer. Its high boiling point makes it a useful material for measuring high temperatures. High temperature thermometers, in that generally gallium is used. Density of the elements increases down the road. This is a regular point. Due to small size of boron, the sum of its first 3 ionization enthalpies are very high. This prevents it to form +3 ions. Okay. The sum of the first 3 ionization enthalpies of aluminum considerably decreases, and therefore it forms Al+3 ions. Aluminum is a highly electropositive metal. In fact, in gallium, indium, thallium, both +1 and +3 oxidation states are observed. Stability of +1 oxidation state progressively increases for heavier elements. Aluminum to thallium it is increasing. Thallium +1 oxidation state is predominant, whereas +3 oxidation state is highly oxidizing in character. +1 oxidation state more ionic than +3 oxidation state. Boron in BF3, number of electrons will be 6, so it is electron deficient. Lewis acid decreases with the increase in the size down the group. BCl3 easily accepts a lone pair of electrons from ammonia to form BCl3.NH3. AlCl3 achieves stability by forming a dimer. You can see this dimer. Values they don't ask, don't worry. For example, the trichlorates on hydrolysis in water form tetrahedral M OH taken 4- species. The hybridization state of element M will be sp3. Aluminium chloride forms AlH2O taken 6+3, where it is sp3d2 hybridized. Aluminium being able to form +3 ions easily, it is more electropositive than thallium. Boron is unreactive in crystalline form. Aluminium forms a very thin oxide layer on the surface which protects the metal from further attack. Amorphous boron and aluminium metal on heating in air to form B2O3 and Al2O3 respectively. With dinitrogen they form nitrates. Very regular points, but important. Boron trioxide is acidic and forms metal borates. Aluminium and gallium oxides are amphoteric. Indium and thallium are basic in their properties. Boron does not react with acids and alkalis even at moderate temperatures, but aluminium dissolves in mineral acids and aqueous alkalis and thus shows amphoteric character. Aluminium dissolves in dilute HCl and liberates dihydrogen. However, concentrated nitric acid renders aluminium passive by forming a protective oxide layer on the surface. Aluminium also reacts with aqueous alkali and liberates hydrogen. This is very interesting. Same amount of aluminium with dilute HCl or dilute NaOH, it will release same amount of hydrogen gas. TLI3 is generally not possible. Okay, except TLI3, it is not possible. This is one interesting question. You see, white fumes appear around the bottle of anhydrous aluminum chloride. Give reason. Anhydrous aluminum chloride is partially hydrolyzed with atmospheric moisture to liberate HCl gas. Moist HCl appears white in color. Tetrahedral MO is taken 4 minus and octahedral MH2O taken 6 plus 3. So this is anomalous behavior we are saying. It can expand its octet. Maximum covalence of boron is 4. Maximum covalence can be expected beyond 4 for remaining aluminum other elements. Boron is unable to form BF6 minus 3 because of vacant d orbitals are not available. So these are the important lines. If you are good at this point, this is not required, don't worry. These are all compounds. This should not be asked. Okay, some uses. Boron fibers are used in making bulletproof vests. Group 14 will take in another video. On a weight to weight basis, the electrical conductivity of aluminum is twice that of copper. This kind of statements you can see in statement 1, statement 2. The use of aluminum and its compounds for domestic purposes is now reduced considerably because of their toxic nature. You can expect this kind of